Okay, now let's define data mining. It's just as a kind of a quick refresher. Data mining is a search for patterns in data using modern, highly automated, computer-intensive methods. Now the key terms here will be search and automated, which is essentially finding hidden information in data. And that's the kind of a paradigm that we will go on at this point, trying to understand the similarities and, in particular, differences between classical approaches and data mining approaches. Now, the reason why we came up with this talk in the first place, and this is not the first time we're doing it, even though we've changed quite a few bits and pieces. The primary reason is that whenever I go to, say, a conventional outfit out there, some kind of team of analysts or journal reviewers or anything, I almost sense oftentimes that sort of strange resistance to accept all of these new methodologies and new methods. There's a large layer of people out there who are perfectly comfortable with conventional modeling techniques, and the GLM being the prime example of that. And at some point, you're kind of facing that wall of resistance when people think that you come here and your job, which is my job, is to destroy their careers or their kind of way of thinking or anything. So what I'm trying to convince the rest of you in these presentations and in our trainings is that this is far from being the case. You can still stay perfectly fine within the boundaries of the conventional statistics, but the use of our tools would unleash some of the extraordinary powers. It's just going to make your jobs so much easier. And even if you're not ready to accept working with these tools from start to the end, and oftentimes you will have reasons that are beyond your control, like in Dave's talk, the regulations, or there's all kinds of structures and requirements out there that may simply refuse to accept anything of that nature as the final solution. But you will be able to use it to your advantage. And I've seen so many people and so many examples when someone, once they've realized the power of all of these individual approaches, ultimately produced a superior models to anything that they could have done on their own beforehand. Let's define these two worlds. I mean, what is it that we're talking about? A classical modeling approach would be collect some data, guess the model, and usually guessing the model either relies on some kind of prior knowledge, or you essentially have no choice. You're saying, let's guess that we have a linear combination of predictors. That's as far as we can go. Use the data to estimate model parameters and to check the model fit to see if you need to modify it or another adjustment is necessary. Now, in the case of Dave's application, that large part of that problem of trying to guess the model was overcome by binning variables into individual ranges. And that's a smart way of doing it. The only difficulty with that approach is that it has limits of applicability. Sooner or later, you're going to fit data sets that hit millions of records and perhaps thousands of variables of varying nature, and not to say the issues of missing values, outliers, and all these other things. But in the conventional scheme, we have no choice. We guess the model. We don't use the data to guess the model itself, and then we only use the data set to evaluate certain parameters. In a data mining modeling approach, the entire philosophy drastically changes. Here, we're assuming large amount of data, no prior knowledge of what the model should be, and we elevate the importance of the data set to the much higher level. We're saying, look, I don't have expertise or competence or even understanding what the underlying model might be. In fact, I could be working in a highly dynamic environment where the signal fluctuates in time, space, etc., etc. So trying to guess what's going to happen is an exercise in futility. And in other words, we're saying, okay, give me an algorithm that will do the job for me. that will start with the data as the initial point and build up the modeling structure on top of that. And I think that to a certain type of individual out there, that's a very big leap of faith. You know, there's a lot of people out there who think that they know what their data sets are all about, and if they see violations in the actual data set from what they think there should be, then they'll blame it on the data set and not on their own kind of preconception. But if you're going that way, it kind of turns everything upside down. You run the algorithm, you see what it finds for you, and then based on that feedback, you make your own, sometimes intuitive decision in terms of whether it makes sense or whether it does not make sense. But the biggest added benefit of doing something like that lies in the fact that if the tool itself allows you to check and view the actual results, then you can enhance your knowledge and turn it around, bring it back to the classical domain, armed at that point with what you have already discovered. So I see many different uses of data mining, aside from the trivial application when the data mining approach is the only thing you use. But you may not be able to pull it off because of a variety of reasons, and regulations, requirements, general acceptance, et cetera, et cetera. But in many cases, that's not the ultimate point. In many cases, you do data mining in order to speed up your own work in the classical domain. So you study the data set, you'll discover all sorts of inconsistencies that might sneak in. You'll discover patterns that at the first glance make no sense in the classical domain. So you study the glance make no sense, and that at the first domain. So you study the glance make no sense, and that at the first domain. So you study the glance make no sense, and that at the first domain. So you study the that at the first domain. So you study 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 that at the first glance domain. So you study that at the first glance